Welcome on this presentation focusing on explaining what is machine learning. We hear a lot about machine learning when discussing data science and discussing predictive analytics and discussing big data. So this presentation will give elements of vocabulary and the basic understanding of what is machine learning. So first we could define the terms. Why is it called machine learning? The first term, machine, is focusing on computers. So machine is a term to express that the fact that the power of computer is going to be used in this technique. So it's not about being about solving a problem with a paper and a pencil. It's very much about data crunching on computers. So that's machine. And learning does it mean that the machines learn as a kid, as a child would learn? No, not at all. It just means that many of the procedures used in machine learning start with a blank state. That is, the algorithms that are going to be used to make predictions or whatnot start with zero accuracy. They are just like completely bad, maybe not even better than chance. But the nice thing about computers is that you can iterate a lot, many times, quickly, over you can iterate calculus calculus basically on a data set many times. So, and each time it's a trial and error process. The first time you apply a calculus on the data set, maybe that the accuracy that you will deduct from it will be very low. But knowing that in the next iteration you can correct what the parameters that you were using, for example, and the next time the accuracy will be slightly better. And you do that again and again. So depending on the size of the data set, depending on the software that you use, depending on the fact that you work on a single machine or on the cloud, each cycle can last a couple of milliseconds or can last several seconds, and you can do millions of them or hundreds of millions of these cycles. At each of these cycles, the algorithm learns. It fine-tunes its parameters up to the point where the accuracy is astonishingly good. So that's what machine learning implies. Algorithms running on computers instead of pen and paper problem solving, and it implies iterations, loops, as you would say, a loop. So the algorithm loops on the dataset. It does one calculus one time and twice and three times, etc. And each time the accuracy increases. So how does it look like to do machine learning? There is a very standard way of using machine learning that you find in every kind of context. First, as a data scientist, you are given a training data set, or you call that a training set. That is data that was collected in the past. So, for example, a list of customers. You have plenty of information on each customer and their credit score. So if the thing you try to predict is the credit score for each of the customers, you have first a training data set where you know the credit score of each customer. So that's very useful because this is the data set that you will use to train your algorithms. This is the data set on which, as I explained on the slide before, that is the data set on which the algorithms will loop again and again. And maybe the first time they're going to loop, so they will number crunch these features that you have for each customer, and it will try to see whether it can predict its credit score. And maybe for the first loop it's going to be so bad at predicting the credit score. But again, machine learning has a huge toolkit of analytical methods and algorithms, and when you apply them, so each of them fits different situations, of course, but when you apply an algorithm to the training set, the algorithm will loop again and again and fine-tune its parameters until it can find for each of the customer its perfect credit score, or nearly so. So that was the second step. You train the algorithms that you find from so many different areas in biology, in computer science, in physics, in psychology, in network science, in natural language processing. You train everything that you have at hand and that makes sense on the training set. Once your algorithms are perfectly tuned to the training set, you bring, well, the real problem that you have, that is the new customers. You know exactly their demographics, their characteristics, but you would like to predict their credit score. So you apply on this fresh data set the algorithms that you had trained before on the training set. And you just cross your fingers that the predictions will be accurate. But since your algorithms have been trained on a similar data set, the training set, things should go well. And finally, you measure the accuracy of your results. You see whether, yes, I should have mentioned that this fresh data that you bring, the test set, is the one where you have, the credit scores. You kept them hidden, but when the algorithm has finished running, you confront the result of the algorithms with the actual credit scores of the customers, and you can see whether the algorithms were correct or not, and you have a measure of accuracy. And then only you can use the algorithm in real life situations, because you will know their accuracy. So a bit of vocabulary here. We say that data scientists train their models or the algorithms on the training set, and then only they test it. They are concerned by out-of-sample prediction, so it looks a bit fancy, but that's actually very important. It means that data scientists, they don't really care whether their algorithms predict accurately the training set, because of course the training set you can you give the algorithms the solution. Since it's a trial and error process, at each loop you can correct the parameters of the algorithm so that it match best and better and best in the next loop, that it match best the data set. So when you run that for millions and hundreds of millions of times, of course at the end you will have a perfect prediction of your algorithms, but that's not too hard to obtain, because you told the algorithms what were the correct values, so that the algorithms could adapt its model. So it could give you the impression that you have an excellent, that your algorithms perform greatly, right? But that would be an illusion, because if you then applied your algorithms to a new data set, the newness of this data set. Maybe it has different logics and different, the data comes from a different situation. Maybe that your algorithms will have a much lower accuracy on this new data set. So the accuracy of the algorithm on the testing, on the training data set does not mean that the algorithms will perform well in test or in real life. So if you have vendor solutions that give you accuracy measures, be very, like we have a 95% accuracy. If they are dishonest, they could actually talk about the accuracy on the training set and not the accuracy in out-of-sample prediction. So out-of-sample just means when you take your algorithm, you leave the training set and you apply it on a fresh data set. Now I'd like to just make the point on how is machine learning so different from statistics. The two are very much related. Machine learning uses a lot of models that come from statistics, but the two are not synonymous. So the first thing is that machine learning does not care about causality. We are not trying to explain why the prediction is accurate. We just want to have an accurate prediction. So the models or the algorithms that that machine learning uses have no underlying explanation of the world or the relations between the variables. You can do whatever works best for prediction. So it can work better than statistics, purely statistical models. The drawback is that if you can predict well, but then if you want to influence the future, if you want to say, well, what should I change in my variables to have an effect I want? Since you don't have a causal model in machine learning, you don't know what you should do to cause the effect that you want. You can't do that with machine learning, and that's where statistics is much stronger. Machine learning, as I explained, has a special concern for out-of-sample prediction. That seems like everybody should be concerned with out-of-sample prediction, but it just turns out that in terms of well, the tradition and the historical path of development of the discipline of statistics, statisticians have been less concerned with out-of-sample prediction than were machine learners. So that's a difference. A third difference is that machine learning picks their methods from a bunch of different disciplines, including a lot of engineering disciplines. So they have a wider scope of inspiration than statistics, which remains kind of a very economic and math-led discipline. It's a discipline where you find a lot of econometricians and math people, but not a lot of linguists or not a lot of network analysts. I mean, more and more, but traditionally that's not the case. And finally, the difference between statistics and machine learning is that statistics is very much driven by these big statistics packages such as Stata or MATLAB or SPSS or the others, Statistica, and these packages are self-contained. They are very hard to deploy or to implement in a big data context where you need flexibility and you need to use custom solutions in order to accommodate the very large data sets that you have to number crunch. So I pointed to the 4 differences between machine learning and statistics. I don't want to stress the difference too much. From my experience, the best machine learners, like the one that win the Kaggle competitions, or if you take just the chief economist at Google, they have a huge training in statistics. So they are statisticians, and then they just expanded their scope of interest. And finally, I just mentioned Kaggle. I like to develop on that. Kaggle is a website that hosts free competitions in machine learning. So I invite you to go and check the website, because even if you don't participate in competitions, it will give you a feeling of what kind of problems can be addressed by machine learning, and what kind of industries launch competitions in machine learning. So you will see that a lot of medical related industries and a lot of advertisement related industries open competitions on Kaggle for anybody to try to predict a lot of different phenomena, from who's going to click on these ads to who's going to have an epileptic seizure. And you should be quite at ease when looking at Kaggle if you want to look at the data sets that machine learners will use to compete. You will always see a training set and a test set. Training, that's the data where the algorithms can improve their accuracy, and the test set is where the competition will happen. The competitors will be evaluated on the accuracy of their models on the test set. Who got the best predictions and who made the least errors in predictions. So, and if you fancy trying it, it's really cool. Anybody can try. So that's it for a very short note on machine learning. Thank you.